Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. At 10:15 a.m. New York time, Tuesday the 4th of July of 1989, I experimentally discovered how and why parallel processing makes new computers faster and makes new supercomputers fastest. And I invented how and why to use that new supercomputer knowledge to build a new supercomputer that encircled a globe and encircled it in the manner the internet encircled a globe. The reason my experimental discovery made the news headlines was that for the 4 decades onward of 1946, the parallel processing machine was a supercomputer hopeful that no supercomputer scientist understood what made it super. The new supercomputer, in turn, gave birth to the new field of computational science. And a new supercomputer gives birth to a new computational science. The importance of computational science was underscored in an article that was in the May 8, 1987 issue of the Chronicle of Higher Education, the flagship newspaper that presents news to universities. That article was written by computer and information technology writer Judith Axler Turner. The article was titled, quote, "Some Hail Computational Science as Biggest Advance Since Newton Galileo," unquote. My 4th of July of 1989 experimental discovery of how and why to use massively parallel processing to solve initial boundary value problems of a new calculus and of the fastest computational physics made the news headlines as the biggest advance in computational science. My world's fastest supercomputer algebraic calculations made the news headlines and entered into the June 20, 1990 issue of the Wall Street Journal. A week later, the computer and information technology writer Judith Axler Turner wrote in the June 27, 1990 issue of the Chronicle of Higher Education that I, Philip Emeagwali, quote, took on an enormously difficult problem, unquote. That enormously difficult problem that I solved and that made the news headlines was the toughest problem in extreme scale computational science. Judith Axler Turner continued in her Chronicle of Higher Education article that Philip Emeagwali, quote, solved it alone has won computation's top prize, captured in the past only by seasoned research teams, unquote. My discovery that made the news headlines back in 1989 was the tipping point of the increasing speeds of the supercomputer. That turning point in massively parallel processing supercomputing of the 4th of July of 1989 led to a new computer. I was asked to explain why American children are writing school reports on my early life in Nigeria, Africa, and on my contributions to the development of the fastest supercomputer. Teaching the groundbreaking discovery of any historical scientist is not mandated in US schools. However, it's included in the guidelines known as the Core Knowledge Series. It's included in Social Studies Standard. Each teacher decides how to incorporate stories about scientists into her curriculum. The computer was not invented by super intelligent aliens from the moon that are disguised as humans. Therefore, the fathers of the modern computer should be studied in schools that use computers. Philip Emeagwali is studied in American schools because I experimentally discovered how and why parallel processing across a new internet is faster than computing within any vector processing supercomputer that was the state-of-the-art technology of the 1980s. Ironically, I am mostly studied in schools in the United States, not in my country of birth, Nigeria, Africa. Historically, if a scientist such as Albert Einstein or Thomas Edison or Alexander Graham Bell is studied in American schools, that scientist will later be studied in schools all over the world. But if a scientist is only studied in schools in Nigeria, that scientist will only be studied in schools in Nigeria. My experimental discovery of how and why parallel processing makes computers faster first made the news headlines in 1989 in the United States, and my discovery story spread to American schools and to newspapers in other countries. The human species evolved from Africa and evolved about 200,000 years ago. The reason our human ancestors discovered was to make their world a more knowledgeable place. Our ancestors invented to make their world a better place. Fire is man's first invention, or rather, man's first discovery. Our ancestors did not discover fire to make the news headlines, but discovered it to make their world better. We discover not to make the news headlines, but to contribute to human progress. For 200 millennia, we discovered to make the world a more knowledgeable place. We discovered to discover new fields of study. The new field that I discovered in the 1970s and 80s is what is now described as modern parallel processing supercomputing. The supercomputer is a witness to humanity's most computation-intensive problems. The supercomputer doesn't just solve the toughest problems. The supercomputer is the modern divining rod for discovering oil and gas. The supercomputer is the crystal ball for foreseeing otherwise unforeseeable global warming. The supercomputer is an instrument for telling the future. I experimentally discovered that the global circulation model running across a new internet, that's a global network of commodity processors that emulates a new supercomputer, can be used to gaze across the centuries. In my home country of Nigeria, that is a member of OPEC, the acronym for the Organization of Petroleum Exporting Countries, their petrodollars is their instrument of national development and poverty alleviation. Oil and gas are at the core essence of Nigeria's sovereignty and identity. My experimental discovery of massively parallel processing that occurred on the 4th of July of 1989 made the news headlines. That discovery of the parallel processing supercomputer entered into the June 20, 1990 issue of the Wall Street Journal and entered as the new supercomputer knowledge of how to manufacture faster computers and the fastest supercomputers. That discovery of the precursor of the modern supercomputer made the news headlines because it was akin to the decipherment of the Rosetta Stone of the unknown world of supercomputers that, in turn, will be used to discover and recover otherwise undiscoverable and unrecoverable oil and gas. The Rosetta Stone was discovered in Rosetta, Egypt in 1799. The decipherment of the writings of the Rosetta Stone enabled historians to decipher the previously undecipherable writings of ancient Egyptians and the writings of Africans that lived along the valley of the River Nile. The Rosetta Stone enabled us to know Imhotep as the father of medicine. The Rosetta Stone enabled us to know that the Pyramid of Giza was a tomb for the Egyptian pharaoh Khufu, who was the second ruler of the 4th dynasty. The Rosetta Stone enabled us to know the pharaohs or the kings of ancient Egypt. My technological quest for the fastest computation began on a sequential processing supercomputer. My supercomputing began in the early morning of Thursday, June 20, 1974. My supercomputing began in the Computer Center at 1800 Southwest Campus Way, Corvallis, Oregon, United States. My supercomputing was my technological quest for the Rosetta Stone that will enable me to experimentally discover how and why massively parallel processing must be embodied within the fastest supercomputer. In 1989, it made the news headlines that I experimentally discovered that parallel computing is faster than serial computing, and in particular, faster when applied to solving the most computation-intensive initial boundary value problems of a new calculus and of the fastest computational physics. Such problems arise and are at the core of computational mathematics and computational physics. In a sense, solving difficult problems in parallel is observed when dogs or lions or humans cooperatively hunt a bigger game or hunt in groups. 3,700 years ago, the Pyramid of Giza in Africa was cooperatively constructed in parallel. That Pyramid of Giza remains the oldest and the only remaining of the 7 wonders of the ancient world. Human parallel processing computing could have been used to solve the grand challenge problem that was posed 4 millennia ago by the African mathematician Hermes and posed in his papyrus. That's the oldest mathematics literature. So the idea of harnessing the power of several commodity processors or computers had been around since the 1940s. However, the massively parallel processing supercomputer was science fiction in the 1940s. In 1946, there was only one programmable computer in the world. The December 13, 1947 issue of the New York Times described that first programmable computer of 1946 as, quote, the only electronic computer among the 4 mathematical brains now in use, unquote. That first supercomputer was at Aberdeen Proving Ground outside Baltimore, Maryland, United States. Fast forward 4 decades from that sequential processing supercomputer of 1946. I was an expert in parallel processing supercomputers who declined a job offer as a vector processing supercomputer scientist at Aberdeen Proving Ground, Aberdeen, Maryland, United States. That first programmable computer was the fastest computer or the supercomputer of 1946. In 1946, the massively parallel processing supercomputer was dismissed as science fiction. The January 11, 1946 issue of the New York Times wrote, and I quote, "Meteorologists contemplate that with enough of these machines," 100 was mentioned as an arbitrary figure, area stations could be set up which would make it possible to forecast the weather all over the world. The United States would be divided into blocks, penetrating into the stratosphere, and every condition which would have any bearing on the weather would be analyzed. Plans for the machine even provide for alarm, which will give a warning if any error in calculation occurred. End of quote. The fastest supercomputer in the world cost the budget of a small African nation. So manufacturing 65,536 programmable supercomputers and manufacturing them in 1946 was as laughable as spending $65 trillion to build a mega supercomputer that's a global network of 65,536 supercomputers. In the 1980s, I was the sole full-time supercomputer programmer of the first and the only ensemble of 65,536 commodity processors that I called a primordial internet. I visualized my new internet as my global network of 65,536 processors that were identical to each other and that were equal distances afar and apart from each other. That internet that I visualized in a 16-dimensional hyperspace became my Rosetta Stone. I deciphered that Rosetta Stone at 10:15 a.m. New York time, Tuesday, the 4th of July of 1989. That experimental discovery of how and why massively parallel computing works made the news headlines and added a new zest or a faster speed and a higher speed up to the quest for the modern massively parallel processing supercomputer. That experimental discovery opened the door to the vast and dynamic field of research called massively parallel processing supercomputing. That modern supercomputer is now powered by more than 10 million commodity off-the-shelf processors that cooperatively solves the most computation-intensive mathematical problems arising in extreme-scale computational physics. I stopped the full-time programming of the most massively parallel processing supercomputers in 1989. I stopped supercomputing and doing so in parallel in 1989. I stopped because I had reached the theoretical maximum speed increase that could be experimentally discovered and recorded across an ensemble of processors that were the building blocks of a new supercomputer. My invention of a new parallel processing supercomputer wasn't finished by 1986. But by 1989, my parallel processing supercomputing was too finished. I wasn't getting any supercomputer speed-up increases after the maximum speed-up that I experimentally discovered on the 4th of July of 1989. And I realized that I have overprogrammed the internet that I visualized as my global network of 65,536 commodity processors. I visualized my ensemble of processors as supercomputing together to emulate one seamless, cohesive internet that is not a new computer per se, but that is a new supercomputer de facto. As a research supercomputer scientist, my focus was on answering the big, unanswerable questions of the 1970s and 80s, and in particular, to answer the grand challenge question of massively parallel processing supercomputing. That grand challenge question was, quote, how do we change the way we look at the supercomputer of tomorrow, unquote. The June 20, 1990 issue of the Wall Street Journal reported that my experimental discovery of the massively parallel processing supercomputer will change the way we look at the supercomputer. In the old way, we thought about a conventional supercomputer as powered by one strong ox. That strong ox was a metaphor for one powerful processor. In the new way, we think about a modern supercomputer as powered by 65,536 chickens. Those chickens were my metaphors for 65,536 processors. In that Wall Street Journal article, it was noted that I experimentally discovered that 65,536 commodity off-the-shelf processors that worked together as one cohesive computing team computed several orders of magnitude faster than one supercomputer that was powered by only one fast vector processor. In the 1980s, I was the strongest proponent for the chickens or for the modern massively parallel processing supercomputer. Seymour Cray, who made his name in the 1980s as the strongest proponent for conventional vector processing supercomputers, was the strongest opponent of the modern massively parallel processing supercomputer. The lesson that I learned from my quest for the fastest massively parallel processing supercomputer was this: the success of a scientific discovery is not dependent on, quote unquote, not guilty verdict from every notable scientist. The science fiction writings of creative writers are different from the factual writings of research scientists. As a research supercomputer scientist, I could not create the fastest computation and create it in the manner a creative writer creates her science fiction novel. I discovered, not created, the fastest computation. I experimentally discovered the fastest computation across my new internet. My new internet was my new computer as well as my new supercomputer. My new internet was a global network of 65,536 commodity off-the-shelf processors. It said that a science fiction novelist is born to tell tales. I said that the scientific discoverer is born to tell truths. Any scientific discovery must be reproducible in a laboratory. My experimental discovery was reproduced by polymaths at home with physics, calculus, and parallel processing supercomputing. My experimental discovery was and can be reproduced because it represented the truth. It's been said that art is what we can get away with. I said that not discovering is what we can't get away with. For 16 years onward of June 20, 1974, my technological vision followed 16 mutually orthogonal dimensions in hyperspace. I followed 16 directions. That vision led me across 16 times 2 to the power 16, or 1,048,576 commodity off-the-shelf processors. Each processor communicated via email in 16 directions and communicated to send and receive initial and boundary conditions for my 65,536 initial boundary value problems and to share those intermediate answers with its 16 nearest neighboring processors. It's by indirection that we discover new directions for scientific progress. In the 1970s and 80s, it was anticipated that Moore's law will come to an end. That means that the anticipated speed increases of processors and computers will not continue to double every 2 years as predicted by Moore's law. With the anticipated end of Moore's law, I anticipated that doubling the number of computer cores will be the only way to double the speed up of the modern parallel processing supercomputer. In the mid-1970s, supercomputer pioneers such as Seymour Cray and Gene Amdahl ridiculed and mocked my parallel processing theory. I theorized that I could use the new internet that I visualized as a global network of 65,536 commodity processors, and that I could use that new internet to solve computation-intensive grand challenge problems. The poster boy of the 20 grand challenge problems of supercomputing was the global circulation model that was used to foresee otherwise unforeseeable global warming. In the 1980s, no automation tools existed for automatic message passing across processors or computers. For that reason, I had to explicitly email each processor that I harnessed to experimentally discover the fastest computation. The supercomputer textbooks of the 1970s and 80s wrote that harnessing the massively parallel processing supercomputer to solve one of the 20 grand challenge problems of supercomputing is impossible. Before my experimental discovery that occurred on the 4th of July of 1989, it was impossible to synchronously email 65,536 commodity processors and command their emails them to compute together as one seamless, cohesive supercomputer that is not a new computer per se, but that is a new internet de facto, and that solved a grand challenge problem in extreme scale computational physics. Since it was believed to be impossible to parallel process, manufacturers of vector processing supercomputers dismissed my parallel processing theory as a huge waste of everybody's time. I theorized that I could use massively parallel processing. I theorized that I could massively parallel process by programming a global network of 65,536 processors. I theorized that I could use those commodity processors to communicate and execute extreme scale petroleum reservoir simulators, and to compute and communicate them faster, and do so by a factor of 65,536 increases in the speeds of both email communication and arithmetical computations. It made the news headlines when I experimentally confirmed my theory and confirmed massively parallel processing on the 4th of July of 1989. That experimental discovery of the massively parallel processing supercomputer now helps petroleum geologists to discover and recover otherwise undiscoverable and unrecoverable oil and gas. That's one of the practical technologies, as well as the rich and fertile consequences that came out of my invention of massively parallel processing. That experimental discovery of massively parallel processing is the reason 1 in 10 supercomputers are purchased by the petroleum industry. Back in the 1970s and 80s, my unorthodox parallel processing approach to supercomputing met a lot of resistance. I was rejected and mocked whenever I proposed that parallel processing will work. In those 2 decades, my massively parallel processing supercomputing premise was that the logic of the grand challenge problem should determine how the problem should be solved, not vice versa. That is, it's only the laws of logic and physics that are sacrosanct, not the technology that in the first place must bend for the laws of logic and physics. In an article dated June 14, 1976, the Computer World magazine interviewed the foremost supercomputer experts that were attending the National Computer Conference in New York. Those supercomputer experts unanimously told the Computer World magazine that the supercomputer theory of parallel processing will be, quote, a waste of time, unquote. In 1989, 25,000 research supercomputer scientists logged on each day onto conventional vector supercomputers. Due to that skepticism and negative press, it was widely believed that parallel processing is a huge waste of everybody's time. For that reason, I was the only person that was logged on each day onto the most powerful and the most massively parallel processing supercomputer in the world. I visualized my modern massively parallel processing supercomputer as my new internet that was powered by a global network of 64 binary thousand processors. I visualized my new internet as married together as one seamless, cohesive whole supercomputer. I visualized my new supercomputer as an ensemble of 64 binary thousand processors that were married together by 1 binary million email wires. In 1989, I was researching alone on how to use 65,536 commodity processors and how to use them to solve one grand challenge problem. In 1989, it made the news headlines that I, Philip Emeagwali, an African supercomputer scientist in the United States, has experimentally discovered how to use a new internet that's a global network of 65,536 commodity processors, and how to use that new internet to solve the toughest initial boundary value problems in calculus and physics. I experimentally discovered how to use my internet as a massively parallel processing supercomputer and use that internet to reduce the time to solution of the most computation-intensive grand challenge problems. I experimentally discovered how to speed up from 180 years or 65,536 days within only one processor to just 1 day across one internet. I visualized that new internet as a global network of 65,536 commodity processors. The two leading lights of sequential and vector processing supercomputing paradigms, namely Gene Amdahl and Seymour Cray, respectively, argued that it will be impossible to experimentally record the speed increase in supercomputing that I recorded in 1989. The 25,000 quote-unquote hot brains or conventional supercomputer scientists at National Science Foundation supercomputer centers stayed with conventional vector processing supercomputers. Those 25,000 supercomputer scientists stayed away from the massively parallel processing supercomputer. And the reason was that each believed that it will be impossible to use 64 binary thousand processors to solve one grand challenge problem. In contrast, I believed that it will be possible to parallel process and to do so when it seemed impossible to do so. Beyond faster computation speeds, using several cores in both computers and supercomputers has rich consequences. One such advantage of multi-core processing technology is that it increased the reliability of the modern computer and improved the fault tolerance of the massively parallel processing supercomputer. A 12-year-old writing a school report on the contributions of Philip Emeagwali to the development of the computer asked me, how do we increase the speed of quantum computers? I answered, in classical parallel computing, I experimentally discovered how to solve all 65,536 challenging problems and how to solve them at the same time, and how to solve them across a global network of 1,048,576 commodity email wires that fed data and answers from initial boundary value problems and fed them to and from 65,536 commodity processors. I discovered how to solve extreme scale problems in computational physics. My physical surroundings entered into my initial boundary value problems of a new calculus and of the fastest computational physics. I'm surrounded by the air and the water that entered into my general circulation models that I executed across my ensemble of 64 binary thousand commodity processors. I was asked, what does a quantum computer look like? I answered, the inside of a quantum computer is one of the coldest places in the known universe. The inside of a quantum computer is minus 273 degrees Celsius. The inside of a quantum computer is 150 times colder than interstellar space. The first quantum computer is not quite a quantum computer. That first quantum computer is a monolithic black box that's 12 feet by 8 feet by 10 feet tall. That first quantum computer fills a small bedroom. The quantum computer will not make the massively parallel processing supercomputer obsolete. The reason is that a quantum computer will not be a general purpose computer. The quantum computer might look like a refrigerator because it needs to be cooled. In quantum computing, the computer memory and the processor must be isolated. I experimentally discovered how to reduce the time to solution from 180 years or 65,536 days within one processor to only 1 day of time to solution across a new internet that's powered by a global network of 65,536 processors. Those processors were used to solve all 65,536 challenging problems and solve them at the same time. I began sequential processing supercomputing in the summer of 1974, and I began by wanting to discover the massively parallel processing supercomputer in 1974. I began parallel processing supercomputing without being able to visualize the modern supercomputer and visualize it in 1974. I began modern supercomputing without being able to even articulate the modern supercomputer and to do so back in 1974. In the 1970s, my grand challenge was to visualize the shape of my internet and to visualize it as a 7,980 mile diameter internet, and most importantly, articulate that internet as the source of the fastest computations, both present and future. But back in 1974, or even in the late 1970s, I wasn't sure how my experimental discovery of massively parallel processing will be contextualized with calculus, algebra, arithmetic, codes, and emails. The reason the speed up of 64 binary thousand that I experimentally discovered made the news headlines in 1989 was that the new knowledge that parallel processing works could not be proven wrong. Like any scientific discovery, my experimental discovery was 100% doubt-free. That experimental discovery was the end product of an acid test type experiment that I conducted across a new internet that's a global network of 65,536 processors. The supercomputer that is 64 binary thousand times faster than the computer is immensely more complex than the computer. I'm often asked, what's the one thing supercomputers can do now that they couldn't do 30 years ago? My answer was this: the fastest supercomputer of today is 100 million times faster than the fastest supercomputer of 30 years ago. The fastest supercomputer is powered by 10,649,600 commodity off-the-shelf processors. Each of those 10 million processors is proof that parallel computing is not a huge waste of everybody's time, as was alleged in the June 14, 1976 issue of the Computer World magazine. 13 years after that negative article in the Computer World, I saved everybody's time by experimentally discovering on the 4th of July of 1989 how to reduce 180 computer years of time to solution to only one supercomputer day of time to solution. I experimentally discovered how to put 65,536 processors, or as many computers, inside one supercomputer. That is, I experimentally discovered a new internet. My experimental discovery was the new knowledge of how computers can compute faster and how supercomputers can compute fastest. I experimentally discovered how to compute faster and how to do so by a factor of 65,536. That experimental discovery of the massively parallel processing supercomputer made the news headlines. That experimental discovery was reported in the June 20, 1990 issue of the Wall Street Journal. That experimental discovery is the reason American students are writing school reports on the contributions of Philip Emeagwali to the development of the computer. Back in 1974, parallel processing was a future computer industry. For that reason, my parallel processing supercomputer research was largely ignored, and I worked alone for the subsequent 16 years. The inventor hid the struggles and obstacles he overcame and hid them to make his invention appear as if it was invented in one brilliant eureka moment. It took me 15 years to invent the new supercomputer that was read in 15 minutes. During those 15 years, I was ridiculed, rejected, and mocked as the bush fowl that crowed in the language of another village. For me, Philip Emeagwali, I defined massively parallel processing as my technological quest for the speed of now from the supercomputer of tomorrow. I did so because the supercomputer of today will become the computer of tomorrow. In my quest for the fastest supercomputer, the details did not matter as long as the ending is happy. After 1989, my massively parallel processing supercomputer discovery became politicized. The obsession of haters was to knock me off my perch. After 1989, a team of American supercomputer scientists tried to steal the credit for the new supercomputer that I invented alone. For the 4 decades onward of 1974, I held those new supercomputer thieves at bay. After 44 years of their rampant criticism and derisions and mockeries of the new supercomputer that I invented alone, that team of thieves started claiming the credit for the new supercomputer that I invented alone. Those thieves told everybody that they invented the new supercomputer that encircled a globe and encircled it in the manner the internet encircled a globe. They stole my original drawings and renamed my new supercomputer from quote unquote Philip Emeagwali supercomputer. They put their names on my invention. My name was completely erased as the sole inventor of my new supercomputer. My invention of a new supercomputer that was comprised of an ensemble of commodity processors that were connected to each other and that were connected as a new internet was stolen by supercomputer scientists who publicly condemned my new internet and mocked it since 1974. To avoid legal prosecution and public shaming, they stole my new invention under a pseudonym or false name. That was the most audacious theft in the history of the computer. That theft brings into question their honesty and moral character. They stole the credit for the invention of my new supercomputer that was a new internet and stole my new technology under a number of false identities and fluid pseudonyms and stole my new computer under a number of throwaway email addresses and throwaway mobile telephone numbers. A paradigm-shifting discovery goes through 3 stages of rejection before its final acceptance. My quest for the fastest supercomputer began on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, United States. 2 years later, the June 14, 1976 issue of the Computer World, the flagship publication of the computing industry, wrote an article that was titled, quote, "Research in Parallel Processing, questioned as waste of time," unquote. Back in the 1980s, my 1,057-page research report on massively parallel processing was ridiculed, mocked, and rejected and was thrown into the trash. That mocked report was the first stage of rejection. On the 4th of July of 1989, I experimentally discovered how and why an ensemble of the slowest processors in the world could solve the toughest problems in extreme scale computational physics and solve them faster than the fastest vector processing supercomputer in the world. I was mocked by vector processing supercomputer scientists and mocked because the internal timer of my front-end computer had a timer resolution of only 1/1,000,000th of a second. For that inadequate timer resolution, I could not reproducibly time my 1/1,000,000th of a second that in turn was needed to time my world record computation speed of billions of calculations per second. It took me 6 months to resolve my hardware timer issue, and indirectly resolve it via algorithms. That internal timer error made my experimental discovery to seem irreproducible, which in turn gave the naysayers a pretext to reject the massively parallel processing supercomputer. In the 1960s through 80s, research supercomputer scientists cited Amdahl's law and supercomputer textbooks when explaining why the massively parallel processing supercomputer cannot be harnessed and why it cannot be used to solve the toughest initial boundary value problems arising in modern mathematics and in extreme scale computational physics. But on the 4th of July of 1989, I, Philip Emeagwali, experimentally discovered that those titans of the world of vector processing supercomputers, such as Seymour Cray, were wrong. The supercomputer textbook was wrong because I experimentally discovered that the impossible to compute is in fact possible to compute, and I did so by using an ensemble of the slowest 65,536 processors and using that ensemble to solve the toughest problems in extreme scale computational physics and solve those problems faster than the fastest supercomputer could solve them. In 1989, that experimental discovery of the massively parallel processing supercomputer won me the top prize in the field of supercomputing and made the news headlines and made vector processing supercomputer scientists that ridiculed, mocked, and rejected me to beg me to become my co-inventor and to become my new best friend. Some went as far as claiming my invention as their invention. In the 1970s and 80s, I was disowned by 4 American universities who each objected to my pursuing my research on the massively parallel processing supercomputer. Today, each of those universities have claimed me as their quote-unquote famous alumni. Rejection is the common denominator of any breakthrough scientific discovery. If the supercomputer scientists of the 1970s and 80s understood my new supercomputer that computes across an ensemble of processors that is a new internet, then that new supercomputer is not new to him or her. And if my massively parallel processing supercomputer research discovery was accepted in the 1980s, then I was not the inventor of that new supercomputer. A discovery that is accepted at first is not a groundbreaking discovery. A discoverer that is accepted by all did not make a groundbreaking discovery. When my experimental discovery of the massively parallel processing supercomputer made the news headlines, I, Philip Emeagwali, the new supercomputer inventor, had no research home other than my apartment. Before my 1989 experimental discovery of how and why parallel processing makes computers faster and makes supercomputers fastest. My country of birth, Nigeria, did not have a frame of reference in the textbook on the history of science. That historical milestone is striking when you realize that technology has improved the standard of living in Nigeria and Africa. My two grandparents at 17 Mba Road, Umudei Village, Onitsha, Nigeria, were never vaccinated. My two grandparents at 6 Wilkinson Road, Onitsha, Nigeria, never spoke into the telephone. My 4 grandparents never saw the Atlantic Ocean that was 190 kilometers away from Onitsha, Nigeria. It's technology that made it possible to travel farther than Lagos, Nigeria, and to send and receive an email to and from the United States to Nigeria. Without that frame of reference of the Nigerian supercomputer scientists that contributed to the development of the computer, studying science and technology in a Nigerian school will be like the Nigerian child watching the Olympic Games for contributions to human progress and then not seeing the Nigerian contingent at the opening ceremony. At 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the U.S. Independence Day, I experimentally discovered the massively parallel processing supercomputer. And I discovered the technology as faster than the sequential processing supercomputer. That supercomputer discovery was equivalent to the Nigerian national anthem being played during the Olympic gold medal ceremony for contributions to the development of the computer. After my 1989 experimental discovery of the massively parallel processing supercomputer, I became the Nigerian that was most searched for on the internet. My experimental discovery of the massively parallel processing supercomputer made the news headlines and caused a sensation within the supercomputing community. Every supercomputer scientist knew that in theory, an ensemble of processors could be fabricated or manufactured. My experimental discovery of the massively parallel processing supercomputer made the news headlines because it was the first time ever that an ensemble of the slowest processors computed faster than the fastest processor that was not a member of an ensemble of processors. For that reason, my experimental discovery changed the way we look at the computer and the supercomputer. In the old way, or in the 1980s, the fastest 500 supercomputers in the world were powered by one powerful custom-made vector processing unit. That is, the old supercomputer computed with only one processor. In the new way, or after my 1989 experimental discovery, the supercomputer is supercomputing with an ensemble of commodity off-the-shelf processors that are identical to each other. My experimental discovery of the massively parallel processing supercomputer is a milestone that made the news headlines because it has rich and fertile consequences. My experimental discovery of the massively parallel processing supercomputer was recorded in the June 20, 1990 issue of the Wall Street Journal, and recorded because it opened a new window in science and technology. Parallel processing is the most important discovery in the history of computational science. The importance of computational science was underscored in an article that was in the May 8, 1987 issue of the Chronicle of Higher Education, the flagship newspaper that presents news to universities. The article was titled, quote, "Some hail computational science as biggest advance since Newton Galileo," unquote. In most of the 20th century, parallel processing was terra incognita on the map of the supercomputer. Since the 1940s, supercomputer scientists speculated that parallel processing could play a role in the supercomputer of the future, but had no idea how to actually parallel process an extreme scale problem in computational physics. It was on the 4th of July of 1989 I experimentally discovered how to massively parallel process the toughest problems arising in extreme scale algebra, modern calculus, and computational physics. Parallel processing has taken the computer into a new era, making the impossible to compute possible to compute. I'm Philip Emeagwali. I've only presented to you a teaspoonful of ocean water, trying to acquire in 60 minutes the knowledge that took me 60 years to acquire. Is like taking a teaspoonful of water from the Atlantic Ocean. Daalụnụ, afam bụ Chukwura Philip Emeagwali. Abụ m onye Ọnịcha. Bịa gafụ m na emeagwali.com ka o mesịa. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.